Okay.
Good afternoon, everybody. So multiple regression, we know how to basically estimate the coefficients. So this is the underlying model, if you remember. So y can be defined by x through some linear model using these coefficients. And we have some error, which is we assume that normally distributed with constant variance sigma squared with and mean 0. Therefore, the expected value of y given x, and as I said, we are interested in the conditional mean. Okay, so given x, because we know that x is a random variable also, but we don't care about distribution of x. Everything that we want to say is given x, what's going to happen. Okay. So the conditional distribution of y given x is this guy. Why? Because the expected value of this epsilon would be 0. And what we are estimating as y hat is basically this guy, x times beta hat. And this beta hat is the basically x transpose x inverse x transpose y. Okay? So what we are estimating is the estimation for conditional expected value. Okay? That's what we are doing. And we said, okay, there is some basically nice properties for this estimator. One of them is the expected value of beta hat is beta. Okay? So it's unbiased estimator. And actually we can show that this is the minimum variance estimator. Okay? So there is a very famous theorem says, as Gauss-Markov theorem says, the variance of beta among all linear estimators is the minimum. Okay, so you cannot, essentially you cannot get a better estimate using any method, better than beta hat. That's what it says. And we know that the variance of beta hat, or the covariance matrix of beta hat, is x transpose x inverse sigma squared, and basically the variance of each element of beta hat, which is C00, C11, C22, in the case that we have two variables or three parameters, then we can use this variance to come up with the confidence intervals for each coefficient and do hypothesis testing at the same time. And hypothesis testing is important because if we say beta j equal to 0 or beta j is not equal to 0, if we fail to reject H null, it means that variable is not important and should be excluded from our regression model. Okay? Any questions so far? Just a quick review. We had a couple of examples, and then we had one, basically hypothesis testing, saying all the coefficients that you have in the model except for intercept are 0 or not. So essentially saying that, okay, the variables that you are selecting or the regression model that you feed it is not doing anything. Okay, it's not explaining any variation. And we can do ANOVA to test that one. We also had one example for that. Next topic is how we can find a confidence interval for this guy. Okay, so expected value of y given x, the point estimate is this. This is the point estimate. It's like mu, the point estimate is x bar. So this is mu, and this is the point estimate. Okay, we know how to find the confidence interval for beta hat, but the question is how we can find the confidence interval for the conditional expected value. And this is the equation given. So this mu hat y given x0 is one simple observation, okay, one single observation. So if you have covariance matrix, so your x0 is one of those rows or any values in that range. Okay? So you can find the point estimate. As I said, the point estimate is multiplying that x by beta, okay? Or your y hat expected value of, let me use the slide notation, y given x0 is beta 0 hat plus beta 1 hat x1 0 beta k xk 0. That's the point estimate. We just plug it in here. We can't find the covariance or the standard error here. This is from table. We can find the lower and upper bound. And as we said, if the point is closer to the center, then we have a more precise, basically, confidence bound. If the point is farther from the center, then we have a smaller confidence bound. I'm sorry, wider confidence bound. Okay? We had one example, and actually I checked, this does not include, this is not among the variables that we had, but it's in the range. So it's not extrapolation. So this is not among these variables, but this is something in the range of these variables. So what we want to do, we have one new observation. So we have one observation. We want to find the confidence interval for the prediction. That's what we want to do in this example. Okay? So first of all, we need to find the point estimate. We already know beta hat. How? From this example. I'll go back. These are the beta hats that we have. Beta 0, beta 1, and beta 2. Okay? What we need to do, we need to replace, plug in x1 and x2 value. So this is x1, this is x2. So we plug it in, we get the point estimate. Okay? Is it clear? Now, we need to find the standard error. So the variance we already estimated before, this is the x, and this is x transpose x inverse. So we multiply, then we get, this is as a standard error. Okay? This is t distribution. So we need to find t, let's say alpha is 0.05. So t of 0.025 and n minus p degrees of freedom. In this case would be, our n is 25, I think, and p is 3. So it's 25 minus 3 degrees of freedom. This number is 2.074. And if we do that, you can see this is the confidence interval for the mean of prediction. Okay? So 95% confidence interval for the mean of prediction. Okay? Is it clear? Any questions? Good? Okay. So what if we want to have a prediction interval, not confidence interval? So what do I mean by prediction interval? If I go back, this equation, I'm trying to find an interval for mu, or conditional mean. Okay? So this is sort of like a mu. But what if I want to find an interval for y? Okay? So if I want to do that, I call it prediction interval. So for the prediction interval, we will use the same equation, but sigma, we add 1 sigma squared. If you compare this equation, you can see sigma squared times this quantity. However, here we have sigma squared times 1 plus this quantity. Anybody can tell me why? Why we are adding 1 sigma squared element here? You can also look at board. The answer is on board. Again, here, this is the standard error we are using. Here, the standard error is 1 plus. So we are adding 1 sigma squared. If you multiply it, yes.
confidence interval the expected value, which doesn't have that extra error term. Now we're doing it on y.
Exactly.
So we're adding in.
That's correct. That's correct. So what we are doing in the confidence interval is on expected value. It doesn't have any error term because the expected value doesn't have any error term. Because the expected value of error term is 0. Okay? Here, you are doing it on y. Y has an error term, and the variance of that error term is sigma squared. So you add that sigma squared to your confidence interval. Okay? Does it make sense? Again, so for the confidence interval, you are trying to have the confidence interval on the expected value or conditional expected value, which doesn't have any epsilon because the mean of epsilon is 0. So you are trying to have the confidence interval for this guy. Now, when you want to have the confidence interval for y, you have one epsilon term. That epsilon term has a variance of sigma squared. So you add that variance to your confidence interval. That's the main reason. So in order to basically separate, they don't call this one confidence interval. They call it prediction interval. But essentially is the same kind of like thing. So this is called confidence interval. This is called prediction interval. Okay? And the reason is we are doing like prediction for one value, not for the mean, for the individual value. Okay, so any questions about confidence interval and prediction intervals? Are we good? Do you know why we have that an extra term? Okay. So now, so let's see. These are the assumptions that we had for simple linear regression or multiple regression. Errors are uncorrelated, random variables with mean 0. Okay, sometimes we say if you want to do the confidence interval, it should be normal. If we don't want to do just point estimates, we don't need the normality assumption. Okay, so either uncorrelated or NID. Errors have constant variance, which means that this sigma squared, okay, for all x's or all pair of y and x are the same. So what I mean is, if you have these data points, so the variance of errors around this is sort of like constant. However, look at this case. So if this is the line, you can see the variance here is smaller, the variance here is larger. Okay? So the variance should be constant. That's one of the assumptions. And errors are normally distributed. And that the third assumption is necessary for just confidence intervals. How we can check those assumptions? We call it model adequacy checking using residuals. You remember? We did it for ANOVA as well. So residuals or EI is yi minus y hat I. In this case, is yi minus x beta hat I. Okay, so basically, you find this line, you find this difference, and this is going to be your residual. And you do it for all observations that you have. So first of all, we start with plotting residual versus predicted variables. So your x-axis is predicted and your y-axis is E. So E versus y hat I. Okay? For constant variance, this is constant variance. Why? Because you can see all points are within a band. This is not constant variance. Again, y-axis is E, and x-axis is your y hat, which is your predictions. As you can see, this is a sort of like a funneling. Small and then large. Similar to this one. A small, then large. This one, again, is not constant variance. A small, large gets a small. Okay? How about this one? What is it? Oh, sorry.
There is a pattern.
There is a pattern here. So the variance is constant, but there is a pattern, which means the independency assumption is not valid. Okay? So if you can see, so there is a band, kind of a constant band, including all the points. Okay? But there is a pattern in the data points that we have. So that's kind of like the band. When I saying band, it's the same thing. But there is a pattern. Non-random pattern. Any questions? Yes?
If you have a constant variance, how does it not conflict with the third assumption, which was the variance is normally distributed?
No, not the variance is normally distributed. Errors are normally distributed. Yes, or error normally distributed means, so these are the values of errors that you have. Okay? So let's say if you project them onto EI, and if you plot the histogram only for EI, not Y hat. Okay? So if you plot the histogram for EI, they should be something like this. Normally distributed. Yes. Any other questions? Okay. So here is the example that we had. So you can see this is residual versus predicted values. It's pretty much constant variance and no non-random pattern. So independency assumption and constant variance assumption is valid. For normal, we do histogram or normal probability plot, which you learn later. So the assumption of normality is good. Is it clear? So this is histogram for residuals, and this is normal plot. You will learn how basically construct this chart. But for now, if these points are around a straight line, then you can assume that the distribution is normal. You just need to know how to interpret that for now. Okay? And you could have box plot. We can use box plot to identify outliers. You remember I told you if you have outliers, it could affect the accuracy of your predictions. It could give you biased, basically, predictors. So let's say all points are here. This is the line. But let's say now one point is here. The line that you get would be this one. If you want to detect outlier, what you do, you plot box plot. And this is, for example, outlier. You find the reason of that outlier if possible. Otherwise, you just exclude it and redo regression. Does it make sense? What else this box plot can tell us? Or let me rephrase my question. What other assumptions I can check with this box plot?
Normality?
Yes. How?
If it's symmetric?
Yeah, exactly. Normality we can check with that. So if it is symmetric, probably it's normal. If it's unsymmetric, it's skewed, so it's not normal. So as you can see, this is Q1, this is Q2, this is Q3. And the length, the difference between Q3 and Q2 and Q1 and Q2 are about the same. So it's symmetric. Any other questions? Okay. So the last part of regression or multiple regression is something we call it coefficient of determination. So basically, it shows how much of the total variation or the variation of data is explained by your regression model. Okay? So we call it R squared. How many of you have seen R squared before? Just raise your hand. Oh, lots of you. So as you can see, that's the equation. 1 minus SSE, SS total. So your R squared is this. If I do the common denominator, that's what I get. So what is my numerator here? Do you remember? What? SS? Regression? Yeah, that's about the same. Because I know what we call the treatment. Divided by SST. Sum of the square of total, which is total variation that you have in your data. The variation explained by regression. The more variation explained by regression, larger R square you will get, which means the better regression model you have. Okay? Does it make sense? So R squared definitely is between 0 and 1. More than 75%. It's good. Don't look at like 95, 99. I mean, those numbers are not realistic. I mean, for homework and stuff, it's fine. But in reality, you should be lucky getting like 75% square. Okay? So I know that most of you have seen R squared. But what is the problem with R squared? That's why we have R squared adjusted, by the way. So what is the problem with R squared? Can anybody tell me? More points, you mean more data points? Exactly. If we add more variables or more predictors, then we get more R squared. Okay? So what does it mean? It means that, let's say y only depend on x1 is a function of x1 and x2. Okay? By adding x3, x4, x5, x6, so these have nothing to do with y. We're just increasing the value of R squared. So by adding some noises, some noise variables, these are noise variables because they don't have anything to do with y. What you are doing, you are kind of like increasing your R squared without increasing the prediction capability. Okay, so that's why they say R squared is not a good model because it's sensitive to the number of predictors that you have. So what should we do? We should sort of penalize, because every time that you are increasing one predictor, you are adding one predictor. What happens? You are increasing the complexity of the model. Okay, so we should penalize adding basically a new variable or normalize it. So that's the way of normalizing it. So what you do, you divide it by the degrees of freedom. So 1 minus SSE divided by degrees of freedom and SST divided by degrees of freedom. This is sort of like normalization, okay, or a standardization. And as you can see, when the number of, so your R squared adjusted is 1 minus SSE divided by n minus p, SST divided by n minus 1. So what happens when p increases, which means you have larger number of variables or predictors in your model. Denominator decreases, this guy increases. Okay? This guy increases. And R squared adjusted decreases. So if you are adding a variable which is not, again, if you are adding a variable which is not related to y, what's going to happen? Your R squared adjusted gonna drops down. Okay? However, if you are adding a variable which basically is related to y, so you are increasing denominator at the same time you are increasing, you are decreasing denominator at the same time you are decreasing numerator, because you are explaining more of variation. That's why it doesn't affect your R squared adjusted. Does it make sense? Okay? Any questions? You good? Okay. So we have some additional material on regression. This part is not going to be on the exam. Okay, this is just good for your projects if you need, or for your future research. This part is not going to be on the exam. Okay, so there are some sort of like a special topics we have. Let's just start with polynomial regression. When you have quadratic form, let's say you want to have this form which is quadratic, or for two variables it's quadratic plus interaction. What should you do? I think we discussed this before. You just need to frame it as multiple regression. For example, let's say this model, I want to frame it as basically multiple regression. I have y, I have matrix X, and I have beta, and I have epsilons. So my matrix X would be 1s, x1, x2. So I define x1 squared as new variable, let's call it z1, x2 squared as another variable, we call it z2, and x1 times x2, we call it z3. So this should be z1, z2, and z3. So we have a new design matrix, which includes intercept, a slope for linear part, and a slope for quadratic parts, and a slope for interaction. And your beta would be beta 0, beta 1, beta 2, beta 1, 1, beta 1, 2, 2, and beta 1, 2. Okay? So it's form of, we can easily transform it to multiple regression. Here is one example. Let's say we have one variable, y and x. These are the pair of variables that we have. And so this is y, and these are x's that we have. We want to basically fit a quadratic model. So the first column is 1, second column is linear, and third column is the squared of, which is the quadratic part, a squared part of a squared x basically. And this is beta. So what we do, we use basically x transpose x inverse x transpose y, this guy, to get the coefficients. And these are the coefficients that we have. So now the question is whether this regression is significant or not. We can do ANOVA. So this is sum of a square of regression. What is the degrees of freedom here? 2. Why? Because it's two variables that we have. Okay. Now we consider x as one variable and x squared as one variable. So this is k. K is 2 in this case. How about degrees of freedom of error? N minus p. N is 10, I think, here. Yes. And p, oops, no, more than that. 12 minus 3, which is 9. And total is 12 minus 1, which is 11. We calculate mean square, which is sum square divided by degrees of freedom. And we calculate f. And as you can see, f is way larger than your threshold. Therefore, model, that x variable should explain your y. Has some information about your y. Okay. Any question on that? Is it clear? So next topic is a little bit new and very, very useful in application. So sometimes, up to now, the main examples that we covered was y is continuous and x is also continuous. Okay? So let's have a table like this. So this is y, this is x, continuous, discrete, or categorical. Let's call it categorical, would be better. Categorical, continuous, categorical. Okay? So if both y and x are continuous, we use multiple regression or regular regression that we have. Okay? Now, what if we have y continuous and x categorical? Can you tell me which tool we can use? Actually, you know that. That's why I'm asking. What? Somebody said something. ANOVA. Exactly. So if y is continuous and x is categorical, do you remember we have factor, and we want to see if that factor is affecting your y? So you can use ANOVA. Okay? Or you can use regression with dummy variables. This is not enough. Let's extend this. Okay? With dummy variables. Okay? So you know ANOVA. I'm going to teach you how to use regression with dummy variables. What if this one is categorical, this one is continuous? Logistic regression. We're going to talk about this today. And how about this guy? No? Again, you can use logistics. That's okay. Logistics with dummy variable. Or you can use something called contingency table. Hopefully my spelling is right. And you learn this, I think, next week, hopefully, or the week after. Okay? So now you know what are the tools that you could use if you want to find the relationship between two variables. Okay? The variables is continuous, you will use multiple regression. This is ANOVA or regression with dummy variable. So let's just start with regression with dummy variables. And we start with simple case where x has only two levels. Okay? So in this case, observation is from operator 1, we use 0. Operation is from operator 2, we use 1. So we basically code these two levels by 0 and 1. That's what we do. Okay? And at the end of the day, so your y is x beta plus epsilon. So your x matrix would be 1, 1, 1, 1 here, and some zeros and some ones. So these are the observations that you collected from operator 1, and these correspond to observations you collected from operator 2. Okay? You may have some continuous variables as well. For example, you can have x2, this is x1, x2, which is 0.1, 0.3, and so on and so forth. So it's, again, multiple regression. The only thing that you do, your categorical variable, you code it by 0 and 1. Does it make sense? Yes.
Values between 0 and 1.
Actually, this is x, not y. Your y is continuous. Yeah. Any other questions? Yes.
So there will be another case if there is order. Like,
So the question is, what if we have categorical, but it's ordered? We have regression for that. If you take regression class, they tell you so how to do it. So it's kind of like ordered regression. And for example, here, logistics is good for when you have y at 2 category. Sometimes it's more than 2 categories. It's called multinomial regression. Again, so This is not covered in this class, but there are tools for that. So let's call it this way. For the categorical data, we have ordinal data, we have pure categorical data. By ordinal data, we mean, for example, level of education. Okay? It could be bachelor, like high school diploma, or master's, or PhD. They are categoricals, but there is some order associated with that. There is a difference. PhD is better than, let's say, hypothetically, it's better than master's. Master's better than a bachelor and stuff. Okay? So they are ordered. How we can do analysis. So I don't think we have a course here in Georgia Tech. I'm not sure. But categorical data analysis is one course, one like a semester-long course. Yeah.
It's basically a correction factor between the two operators.
Yes. Yes. So it basically captures the effect of operator. That's why I'm saying it's similar to ANOVA. In ANOVA, we were using tau to capture the effect of basically factor. Here we are using beta. Yeah. They are one-to-one correspondent. Any other questions? Okay. Now, how about if the case that variables have 3 levels or more? I will answer this question later. But let's start with one example. Your Y variable is surface finish in a machining process. Your X1 would be your, let's say, I don't know, let's introduce, I want to see what the X1 is. Yeah, RPM. And your X2 is the different tool type. Okay, so you have 2 tools, type 302, 416. You want to see whether a speed or RPM and tool type can be used to predict your surface finishing. Okay, so you collect data, you do machining on 20 parts, and you measure the surface finish. That's the speed, and that's the tool that you use. So for half of them, you are using cutting tool of type 1, and for half of them, you use cutting tool of type 2. So we use 0 to indicate 302, and we use 1 to indicate 416. Can we switch that? Yes, we can. It's just arbitrary. Any questions so far? So the design metrics, now you can see the first one is all ones because this is intercept. The second one is for RPM. And third one, half of them is 0 because it corresponds to 302 tool, and half of them is 416. Should we like always should be half and half? No. Any proportion should be okay. And then we have Y. So you can use again X transpose X inverse X transpose Y with this basically design matrix, and you can get your beta hat. In this example, your beta hat would be 14.27. This is for intercept. This is the effect of X1, 0.14, and this is the effect of X2. Okay? So what does it mean? So let's say we are using tool type 302. In this case, your Y hat would be 4.27 plus 0.14 X1 plus. So what is X2 associated with this? Is 0. Nothing. Okay? And when you are using type 4, what was that? 486? 416. 416, your X2 associated with this is 1. So it's 4.27, 0.14 X1 minus 13.28 times 1. This is also 13.28 times 0, which is 0. Okay? Now you can see this is the effect of tool. So if you change from 302 to 416, that's the reduction that you get in your surface or response variable. Okay? Does it make sense? So this is your baseline. When everything is 0, that you have your intercept is your baseline. Then you have some variables at 1, then your intercept changes. That difference shows the effect of that variable. Does it make sense? Yes, question.
The categories, since
So
our beta will
the question is, for example, can we switch this? Oh,
like if we have
no, there is. Yeah, you need to basically, you can use any number that you want, but the interpretation is going to be very difficult. You know, for example, if you use 2, you need 2 and minus 2, let's say. Then you need to basically consider that there is a 4-unit difference between these two because it's minus 2 and 2. Or if you use minus 1 and 1, then you need to consider there is like 2-unit difference between them. So it's not as straightforward. So that's why I recommend to just use 0 because it gives you a baseline, and 1, this is just 1 unit. It gives you the effect. Do you remember I told you what is the interpretation of x1 here? I'm sorry, that beta 1 here. If you change x1 by 1 unit, how much your response is changing? I can exactly say this one for this guy. But if my category was minus 1 and 1, I couldn't do the same, basically, interpretation. Okay?
unit that applies to the variables, or is it just safe to use 1 and that's the standard?
So if you use, for example, 2 or 3, that's what you're saying. So you code one of them with 2, the other one by 3, or 1 and 2. I think in terms of effect, that's going to be the same if you want to find the effect. But in terms of what do you mean by scaling categorical? I don't know.
Change it.
Oh, yeah,
Affecting
you need to do the scaling for interpretation. Yes, if you use different category. But don't make your life harder. Yeah, just use 0 and 1. I'll tell you. I'll tell you what to do. Exactly. So that's basically the question I had here. What if we have more than 3 levels? Okay. What if we have, actually, so this is different. What if we have 2 variables? What if we have 1 variable more than 2 levels? That's 2 different things. Okay. So if you have n variable or k variable, but all of them are at 2 levels, okay, so you code them exactly with 0, 1. That's it. All k variables. So you add another column of, so let's say in this example, we have another categorical variable. You add another 0, 1 here. Another one. Okay? But the question is, what if I have 1 variable or 2 variables with more than 2 levels? Okay? Then we use more than 1 dummy variables. So here is what we do. Let's say we have 3 levels. Then what we define is, so this is your matrix. Okay? Let's say A, B, C. I use D1 and D2, 2 dummy variables. Okay? If it's at level A, both of them are 0. If it's at level B, this is the combination. If it's at level C, this is the combination. Does it make sense? Yes.
Or could you do a polynomial to capture if you have a 3-level or second order, like a quadratic?
No, if this is something else. So can we have a quadratic effect for categorical variable? That's
Second column would be the square of the value.
Yes. So what you can do then, you could basically go, that's a little bit tricky. So what you have, let's just start with 0 and 1s that you have here. So for this one, x squared and x are going to be the same thing, okay? But here, if you want to have x squared, then actually I don't know. Let me think. I need to think how we can. I don't think with the dummy variable we can capture that. But there is a way to do that. Let me finish this and I think about that. Okay. So let's say right now we are talking about linear variable. Okay. So if we have 3 categories, yes.
If it's a single valid reload, then
No, but the thing is, sometimes what you have, the effect is 0, 1, or let's say low, 0, and high, and your y is something like this, rather than this. That's what it's saying. So this is your y, and this is the categorical. So you cannot capture it by linear. So we can capture that by, for example, quadratic model. But I don't think this way can help us. I need to think how we can do that. Okay? I'll get back to you on that. So we have different categories, A, B, and C. Okay? And we have 2 dummy variables. What if we have, let's say, k levels? How many dummy variables do we need? K minus 1 dummy variables. Okay? And we arrange them like this. Whenever it is at level A, we use 0, 0. Whenever it's at level B, we use 1, 0. Whenever it's at level C, we use 0, 1. D, we need to have one more. So, for example, A, B, C, D would be 0, 0, 0, 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay? That's for 4 levels. So before I let you go, one question. Why don't we use 3 dummy variables? Let's say A, B, C, I can say this is 0, 0, 1. This is 0, 1, 0. And this is 1, 0, 0. No linear independency? What do you mean? This is full rank matrix. They are independent. You are right though. But not on this matrix. So the problem is this matrix should be fine, but your X matrix is not. Because your X matrix, you have 1 at the beginning. So you have 1, 1, 1. Okay, so you remember your X matrix when you have intercept, everything is 1. Now if I put these together, then there is a clear linear dependency on the column. For example, if you add these 3, you get this one. Okay? So what is the problem with that? X transpose X going to be singular. So you cannot do inverse. Okay? Therefore, we just get rid of one of them. And that's why this guy represents the baseline, which is the intercept. Okay? Does it make sense? Okay. I think I'm going to stop here, and we have logistic regression for next class. By the way, exam going to be on Friday. Exam is comprehensive, but I will focus on the topic that we covered after the first exam. So there is no direct question from likelihood and stuff. But you may need to know some knowledge for the first part to be able to answer all questions. We will have a review session on Wednesday. Okay? I will see if I can finish the goodness of fit. I may include the goodness of fit, but I'll tell you on Monday. Okay?